Okay, ladies and gentlemen, hello everyone. We're finally back with the series of webinars on integrated quantum photonics, and we are happy to introduce our next talker, Dr. Massimo Borghi, from NanoScience Laboratory of University of Trento, Italy. He has done his postdoctoral research in this same university, and he will talk about shaping and measuring quantum states of light with silicon photonic chips. Please, the stage is yours, Dr. Massimo Borghi.
Thank you very much for the introduction and for the invitation. I'm sharing my screen. Okay. Can you all see my screen?
Yes.
Okay. So, as Gor said, I'm working at the physics department of the University of Trento. So Trento is a city in the north of Italy, and okay, just try to. Okay, so as you can see, these are some of the most significant places, let's say, of the university. This is called the Polo Ferrari, where the students are having their lectures. This is a picture of the students, of course, before that COVID happened. And as you can see from also, okay, I have to activate. Okay, as you can see from also this this view, which has been taken from the table tennis field that we have in our physics department. You can see the mountains on the background, so mountains are really close to here. And of course, this is the table tennis field. And I'm part of the NanoScience group, which involves around 25 people spread among researchers, PhDs, master students, and so on. So as you can see, I'm sitting on this table here. It's just because this picture was taken before I joined the group for the second time. And the head of the lab is Professor Lorenzo Pavesi. If you're interested in knowing more about us, about our facilities, or about the members, you can visit this link, which is the link to our website. So what we do. So as you can see from this picture, where we have a very young Professor Pavesi, that is indicating what I think it's a silicon photonic wafer. Actually, I don't know if this is something else, because I don't know where this, when this picture was taken, but we do silicon photonics. So it's a technology, as you might know, which aims to fabricate photonic chips at wafer scale. And if we have more or less as it happens for the microelectronic devices, if you zoom in and you reach the die level, so to single chips, you can see on these chips that we can arrange hundreds of optical components like pin splitters, phase shifters, filters, and so on, which have a dimension which is at the scale of tens of micron. And since silicon photonics is a quite broad topic of research, we are specialized in some of them. So we have a new, quite brand new activity on neuromorphic photonics, and then a well and long-term established activity on nonlinear optics, and of course on integrated quantum optics. So I put integrated in brackets since we have also a line of research which performs quantum optics experiments in bulk. So this will be the main topic of this talk. So integrated quantum optics. So you can see in this slide the approach that we typically do with integrated optics to build quantum photonic architectures for, let's say, general purpose quantum photonic architectures, which can be used for simulation, computation, and so on. And this is, on the other side, the bulk optics way, which I like to call them the hero experiments. As you can see, so in an integrated chip, so this is a representative of the state of the art now. In this integrated chip, which has a size of a few centimeters square, we can host hundreds of reconfigurable units and in a very small compact footprint. And you can immediately tell that the integrated optic approach with respect to the bulk offers an improved stabilities, of course, of all the optical paths, a major scalability, and also it's a low power consumption in terms of the tunability of these elements. And the silicon photonic platform is not the only technology that has been pursued for quantum photonics. So indeed, the first experiments were have not been done in silicon, but in silica circuits. But as you can see from this table, so silicon is getting a quite high score in most of these fields, which are the density, the loss, the possibility to engineer passive devices. But it has a quite low rank for what concern the photon sources, and as we will see later. So this is a general view of a silicon quantum photonic chip. So the general aim is to build a monolithic architecture which can host all the necessary components for doing some useful computation. So we have a first stage where we have qubit sources. So of course, the qubits are encoded in single photons. We can use different degrees of freedom, like the spatial mode, or the polarization, or the time bin, to encode the two states of the computational basis of the qubits. And regardless of them, this stage is followed by a reconfigurable stage where we have quantum gates, where we process information, and then a readout circuit where we can have the heterointegration of single photon of superconducting nanowires detectors, for example. This talk will mainly focus on the qubit sources, silicon qubit sources. So in silicon, the process that is used to generate the carrier of qubits, so photons, is called spontaneous four-way mixing, and it's a third-order nonlinear process. Basically, what happens is that we shine the material with a bright coherent pump. We can have typically a power which is of the order of magnitude of 1 milliwatt of 1550 nanometer, which corresponds to 10 to the 16 photon per second. And these devices, which can be resonators, or we can have a spiral. So this is silicon, which has been lithographically shaped into waveguides or ring resonators. And this device helps to confine light and to enhance them to help this nonlinear interaction to occur. And what happens is that due to spontaneous four-way mixing, with a very low probability, we can have that two of these photons belonging to the bright field of the pump are annihilated, and two new photons emerge with different, in principle, frequency, which are called conventionally the signal and the idler. So these photons will form the basis, the substrate for the computation that we will describe later. This is a really weak process because the nonlinearity of the material is weak. We have about 12 orders of magnitude of difference between the photon flux of the pump and the flux of the photons which are generated. This process has to obey the usual energy and wave vector conservation relations, which states that the energy of the emitted photons of the signal and the idler must be equal to the sum of the energy of the pump photons, and also the wave vector has to be conserved. The energy conservation is ensured if we annihilate two identical photons, if the signal and the idler are symmetrically located with respect to the pump. You see that if you sum this energy and this frequency and this frequency, you obtain twice the frequency of the pump, and so energy conservation is satisfied. While if these photons are generated not too far from the frequency of the pump, up to the first order, also the wave vector is satisfied. So this process is efficient and it can happen. So more specifically, what is produced by spontaneous four-way mixing is not just a single pair of photon, but we have what is called a two-mode squeeze state. So two-mode squeeze state means that we have to apply this exponential operator, which is called the squeezing operator, which creates photons in the signal and the ideal modes to vacuum. So probably it's more instructive to illustrate the shape of this, the structure of this bosonic field using the Fock state representation. So the representation in terms of the eigenstates of the number operator. So we see that two-mode squeeze state is just a coherent superposition of states which have different numbers of signal and ideal photon. What is really interesting and peculiar of this state is that the photon number of the two modes is correlated. So if we have one signal, we have one ideal photon. If we have two signals, we have two ideal photon, and so on. So this is just a pictorial view which shows that one photon is always coming out with the other partner. One thing that I forgot to say is that this emission is the emission of the signal and the ideal photon happens at the same time. So what is interesting, and it's very interesting to exploit this peculiarity because we can use the photon number correlation to herald the single photon Fock states. What we do is the following. We generate the two-mode squeeze state from a source, which can be, for example, a ring resonator in this case. And then we can use a wavelength selective device like a dichroic filter, which separates the two modes depending on the wavelength, so another degree of freedom. And then we can use this in combination with a photon number resolving detector to herald the other photon into a specific Fock state. So for example, if our detector is clicking and giving us an amplitude which corresponds to one photon that is detected, it means that due to the number correlation, the heralded photon of the other twin photon is exactly in a single photon Fock state. While if we detect two photons, we have an heralding of two photon Fock states of the other partner, and so on. And this is the key building block, so heralding of single photons, because we can encode qubits within these single photons. So the next step is when we have the ability to herald single photon, the next step is to do something with them. And the most basic experiments that we can do is to let these photons to impinge to the opposite to the opposite ports of a beam splitter. This is the basic quantum optical experiments that we can do, but it's, as we will see later, at the heart of every gate, at every basic gate, from which we can build every quantum photonic architecture, universal quantum photonic architecture that is based on linear optical elements. So it's a key to understand the behavior of this experiment and how the metrics of this photon influence the outcome of the experiment. So when we do this, we have four possibilities, four possible paths. So the two photons both are transmitted by the beam splitter. The two photons are reflected by the beam splitter, and this ends up with states in which we have photons on both sides, on both parts of the beam splitter. So they are indistinguishable from the point of view of an experimentalist that would like to try to understand which pattern is generated at the output of the beam splitter. And then we can have that one photon is reflected, the other is transmitted, and the symmetric case. So due to the fact that the transformation operated by the beam splitter must be unitary, the reflected photon in this optical path must acquire a pi phase shift with respect to the one that is reflected on the other side. And so we can see that we have two indistinguishable paths that have a phase of pi between each other. So these will undergo destructive quantum interference. While these paths are distinguishable, so they are not interfering with each other. So this means that the outcome of this experiment is to have both photons which are bunched into one port or in the other port of the beam splitter in a coherent superposition. And so if we try to measure the coincidences between these two detectors, the two detectors will never click together. The typical experimental signature of this is called the Hong-Ou-Mandel dip. So if we monitor the coincidences at these two detectors as a function of the time separation between the two photons, we observe this shape. So here we have that in this dip, the two photons are arriving at the same time on the beam splitter. And so they are undergoing this destructive interference, and they will never emerge on the they will never induce anti-bunching states. So we observe a dip in the coincidences. While in these tails of the distribution, the two photons are separated in time. The time arrival of the two photons is large, and they will never impinge on the same time and on the beam splitter, so they will not undergo this kind of interference. And so we will not observe a lack of coincidence. So the next case is to examine what happens to this experiment when we do not generate herald photons which are equal to each other, but we, due, for example, to fabrication imperfections or whatever reason, the two sources are emitting photons, are heralding photons, which are distinguishable. So we can again repeat the same experiments, and we have again the four possible outcomes, but this time the two anti-bunching terms that you can see on the top are no more indistinguishable between each other. And this can be easily shown by the fact that we can, in principle, think to place an interference filter in front of the two detectors, and which let pass just a particular type of photon. It can be, for example, a different color. And we are able, by placing this interference filter, to precisely determine if which pattern of photon distribution has occurred at the output ports of the beam splitter. So the main result is that if we have distinguishable photons at the input of the beam splitter, we don't have just the bunching terms, as I said before, but we also have anti-bunching terms where we can have one photon at the output of one port and one photon at the other output. Now let's go a little bit more in detail and introduce some elements of reality. So because the examples that I did so far are for ideal sources. So this will introduce us to the concept of purity. So as I said before, the process of spontaneous four-way mixing is governed by wave vector and energy conservation. So the wave vector conservation can be cast into this form. I just replaced the expression of the wave vector as a function of frequency and the refractive index of the material. And up to the first order, we can neglect the dispersion of the refractive index. So we can simplify all these terms, and we end up to the energy conservation relation. So energy conservation ensures wave vector conservation and vice versa. Rearranging this term, we can express the frequency of the signal as a function of the frequency of the idler and the one of the pump. And we see that there is an anti-correlation between the frequency of the signal and the one of the idler. So this is the line that I shown in this equation. In this two-dimensional plot, it's shown the probability of generating a signal and the idler photon with a given frequency. And you can see that most of the light which is generated lies on this anti-diagonal line. Here we can see that at a certain point, even if the system obeys energy conservation, we have no more generation of photons. And this is due to the fact that we are far from the frequency of the pump. And so the first order approximation no more hold. And the second order dispersion is making the phase matching relationship to no more hold again. And so the most important result is that both the signal and the idler photon are no more generated by the source in just a specific color, in a specific mode, but each can be described by a probability distribution. So the marginal distribution is no more a Dirac delta, but it's a continuous distribution of different frequencies. So this will be the more correct expression of the term of the squeezed state, which describes a pair. So one signal and one idler photon. And then the second most important point is that the probability distribution, the joint probability distribution of the colors of the two photons is not separable. So we can see that this Gaussian is elongated along the anti-diagonal of this plot. So it cannot be factorized in the independent probability distribution of the signal and the idler. So this is just an example. This is the familiar expression of a rotated Gaussian probability distribution, which has a covariance matrix, which is not diagonal. It has also some off-diagonal terms which express the covariances, which makes the state not separable. But of course, we can always perform a rotation of the coordinate frame, which brings our initial probability distribution. So in this original coordinate frame, the two frequencies are correlated. If we perform a frame rotation, we can make the joint probability distribution to be separable. So here in this case, it was simply sufficient to rotate the coordinate frame by 45 degrees. But this is, of course, just a didactical example. So in this new coordinate frame, it's just sufficient to choose the transformation matrix between the two variables, so between the old and the new coordinate frame, in such a way that the covariance matrix, so the covariance matrix, sorry, is diagonalized by this transformation. So in the new coordinate frame, this becomes effectively a separable state. So this is just an intuitive view of the fact that it exists a general decomposition, which is called a Schmidt decomposition, which says that we can always express an arbitrary function in the sum of the product of independent functions, one in this case for the signal and one for the idler, in very similar way to what I've shown before with the change of the coordinate frame for a Gaussian. So by inserting this expression into the operator, which creates a realistic squid state for our sources, it turns out that we can arrange this term and write the state which is produced by the source as a tensor product of n independent and orthogonal squeezers. So this is the expression of the field. You can recognize that here we have a tensor product, and each element of the tensor product is a two-mode squid state, as the one that I've shown in the beginning, where the signal and the idler had a well-defined mode, and the photons are created in Schmidt modes. So this is the analogy. So a two-mode squid state, it can be expressed as a single source which is emitting a signal and an idler in a well-defined mode, while a realistic source is the tensor product of many of them. So a single source becomes equivalent to a parallel of n sources. Each source is representative of a Schmidt mode. Each source is emitting a two-mode squid state, which is in a particular Schmidt mode. And then all these Schmidt modes are combined into the same spatial mode. For example, it can be this waveguide in such a way that, for example, just the single pair term is now not just the sum of a single mode, but we have a collection of them. So we can have a pair that is emitted by, in the first Schmidt mode, if just this source is firing, or to the second Schmidt mode if this second source is firing, and so on. So now that we know how to represent a realistic single source as a collection of n independent sources, each emitting a different Schmidt mode, we can understand what happens when we let to interfere two of them. So the first, it's better to introduce what happens when a source that is not pure is used to herald one of the two photons of the state. So we have in this example, I shown a source which can be represented by which has just two Schmidt modes, and then we use again a dichroic filter to separate one photon of the pair, let's say, based, for example, on the color. And one important thing to have in mind is that the single photon detectors are not able to distinguish between the different Schmidt modes. So if we detect a click here, the heralded photon will be or into the first Schmidt mode or into the second one. And I would like to place your attention to the fact that this state is mixed, is not a pure state. So this means that it's different from the state which is obtained by a coherent superposition of the first Schmidt mode and the second Schmidt mode, because this will have a density matrix which contains also coherence terms, and which is of course different from this one. So when we have two sources which are not pure, so both can be represented again by two mode squeezers, each in an independent Schmidt mode, we herald one of the photon of the pair and we let the other partner to interfere into a beam splitter. Now we have a plenty of possibilities. So the heralded photon can be both into the same Schmidt mode and give rise to the four optical paths that I discussed at the beginning. Then we, of course, the same can occur for the second Schmidt mode, while we can also have cases where one photon is heralded in the first and the other in the second Schmidt mode. And since these modes are orthogonal, so are distinguishable between each other, they are not undergoing completely destructive interference, as in the case that I discussed. So these terms, which involves the same Schmidt mode, every term is generating the same Ongo-Mandel dip with a 100% visibility, while these terms are reducing the visibility because they are distinguishable. They are not interfering to each other. So the result is that if we compare the Ongo-Mandel dip that we obtain for pure photons, which goes to 0, so 100% of visibility, as we decrease the purity of the state, for example, this is 75% of purity, the visibility drops. And the residual coincidences that we observe in this plot when we have zero delay between the two photons is representative of the fact that we have still anti-bunching terms. And so photons can exit on both sides of the beam splitter and give rise to a coincidence. So this is in order from right to left, a not ideal source which interfere very badly on a beam splitter towards ideal sources. So the not ideal case is when photons are distinguishable and not pure. While the best case, when we can observe a Ongo-Mandel dip with 100% of visibility, is when the photons are indistinguishable and pure. But the fundamental question that now arises is, okay, I introduced the concept of purity and of indistinguishability. I say that it's important to have high purity and high indistinguishability to have an Ongo-Mandel dip with a high visibility. And it's important to suppress the anti-bunching terms, but why we would like to do that? So to give an exhaustive answer to this question, it will take probably another talk or a series of lectures. So I will just try to give an hint, an idea on why this is important. And the fact is that the Ongo-Mandel effect and the capability of realizing a complete destructive interference of the anti-bunching term is at the heart of building the basic gates through which every computation, every scheme, every architecture for linear optical computation with photon is based on. So these are some examples of seminal papers which propose universal schemes for quantum computation using linear optical elements. I would like just to focus on two of them. So this is the famous work of Knill, Laflamme, and Milburn, which propose it's like this the circuit approach to quantum computation, while this is the cluster state measurement-based quantum computation. So in both of this scheme, we have fundamental gates over which we can build the substrate, the fundamental substrate. So for example, in this scheme, a fundamental gate, which is one of the set of the gates that are universal for computation together with single qubit gates, measurements, and classical feedback, is the so-called conditional sign flip gate, or CZ gate. In this gate, we have two photons, which if they enter into these middle modes, they must exit bunched at the opposite side of this bin splitter in order for the gate to succeed with 100% of fidelity. And this is only possible if here we have a perfect, we observe a perfect on-Gummandel dip. So two photons will emerge in this port and two photons will emerge in the other port. This is a similar situation. So this is a picture of a cluster state. Every vertex of this graph is representing a photon in a plus state. And then these edges are conditional sign flip gates. And these gates can be done with linear optical elements with using this arrangement of bin splitter. And again, we see that we can build this cluster only if we can interfere two photons at the bin splitter and give raise to 100% visibility of the on-Gummandel dip. So now let's come to the way we engineered the emission of silicon sources, which are pure and indistinguishable in our work, in our last work. So the way we achieve that is by a particular class of spontaneous four-way mixing, which is called intermodal spontaneous four-way mixing. As we saw before, when we have a four-way mixing approach where all the modes or the photons are propagating into the same mode order, we give rise to joint spectral intensity, which is strongly correlated along the anti-diagonal. While we can demonstrate that if we let these photons to propagate into different mode orders, we can engineer the phase matching dispersion in such a way that the phase matching band is much narrower than before. And so this is helping to shrink the joint spectral intensity into a more circular shape, which is more separable than this state. So we are increasing the purity. But still we see that we have this small correlation along the anti-diagonal, which are called the sinc lobes, which are not removed, even by going to intermodal four-way mixing. So how we can remove this correlation and why they appear? So in order to understand that, we have to consider the fact that in this approach, we can generate photons only inside the waveguide. So outside the waveguide, the interaction is the nonlinear interaction, so spontaneous four-way mixing has a strength of 0. Then it changes abruptly to some value, some strength within the waveguide, and then no generation occurs, of course, at the output. So this means that if we compute the joint probability distribution of generating a photon at position, for example, the signal photon at position ZS and the ideal photon at position ZI, it must be equal to 0 outside the waveguide. So when these coordinates are both lying outside the waveguide, and different from 0 in the waveguide. So this means that we have a box shape wave function. If we Fourier transform this and we go to the wave vector space, which is just the ordinary joint spectral amplitude, this is possible only if we add the side lobes, the sinc lobes, because the Fourier transform of a box is a sinc. So this is where the lobes are coming from. And we can get rid of this by adopting a peculiarity of the intermodal for a mixing approach. So we can exploit the fact that different mode orders travel with different group velocities. In particular, the fundamental mode is faster than the second order mode. So if we impose a time delay, so if we retard the fundamental mode with respect to the second order mode, and then we let these two to enter into the waveguide, this is what will occur. So the two pulses will gradually overlap only within the waveguide, and it will have a maximum overlap at the center of the waveguide. And then the interaction will switch off gradually. So we have realized an effective interaction between the pump and the signal and the idler photon, which has a Gaussian shape. With respect to before, the interaction, so with before I mean a configuration where the two pump photons are not retarded between each other, we shifted from a configuration where the interaction suddenly jumps from 0 to some value to an adiabatic turn on and off of the interaction. And so, since the Fourier transform of a Gaussian is another Gaussian, we have removed these sinc lobes. How we implemented this on a photonic chip? So we inject the pump, split them into two optical paths. One is delayed, the one which is referring to the fundamental mode order. And then one of the paths is converted into a higher order mode. So as this spiral is excited by both the fundamental and the higher order mode, which are delayed in time. The interaction occurs in the middle of the waveguide. Photon pairs are generated, and they will separate it based on their color at the output of the spiral. So this is a picture of the photonic chip, and this is the way we characterized the joint spectral distribution. So once that we generate the signal and the idler, we pass them into tunable filters, which select the peculiar frequency of the signal and the idler, and we monitor the transmitted photons in coincidence. So this is the reconstructed joint spectral intensity, which shows a nearly circular shape, which is a signature of the lack of correlations between the two photons. Sinc lobes are not present, and so the purity is quite high, is estimated to be 99%. And since we are using multi-mode waveguides to achieve this, which are 2 micron wide. So for a high index contrast platform as silicon photonics, this is a quite large waveguide. It's really robust against fabrication imperfections. And so if we place two spiral sources nearby on the chip, this is around 100 micron of distance, the two sources will emit photons which are nearly indistinguishable. As you can see from the tomography, which is performed on the source 2 and on the source 1. The indistinguishability between the two is 98.5%. The last step is to make the heralded photon to interfere, so to perform the same, the heralded Ongu-Mandel experiment. This is done by sending the two heralded photons into Mach-Zehnder interferometer and scanning this fringe. So with respect to the scheme that you have in mind, where here you have a beam splitter with 50-50 reflectivity and the transmittivity, the Mach-Zehnder can be thought as a function of the phase as a beam splitter with variable reflectivity and transmittivity. And so, for example, it can be configured with a phase of 0 to totally reflective, with a phase of pi to totally transmittive, or to a 50-50 beam splitter. So as we scan the angle, we get this coincidence pattern between these two photons. So when we have pi half of the phase, the beam splitter is 50-50 beam splitter. And so since the two photons are identical and pure, we have just anti-bunching terms, so two photons at this port and two photons at this port of the beam splitter, and so no coincidences are observed. And of course, when the beam splitter is totally transmissive or reflective, we recover the coincidences. So the visibility of this Longo-Mandel dip is 96%, which is a record for two photons that are heralded on the same chip from different sources. So now it's time to introduce the second topic of this talk. So we have seen that a lot of information can be gathered from the measurement of the joint spectral intensity. So the joint spectral intensity is this plot here, probability of detecting a signal in an ideal photon as a function of frequency. So the setup that I shown to measure this kind of frequency correlation assumes that we send the signal in the ideal into tunable filters, which fix which slot we are probing in this two-dimensional plot, and then wait for coincidences to accumulate to reach the desired signal-to-noise ratio. So I just place here random numbers which are proportional to the probability of a photon pair to fall within one of these blocks. And then by scanning all these blocks, we can reconstruct the shape of the joint spectral intensity. But this is an approach which is time-consuming because the photon flux is really low due to the weakness of the spontaneous photomixing process. And also because if we want to make this very resolved and very high, with a very high signal-to-noise ratio, we have to decrease the width of these, the size of these blocks. And this is also scaling down the amount of photons which will fall within this window, within this spectral window. So how we can speed up the procedure of measuring a very accurate joint spectral intensity? The solution is to use another approach, which is called stimulation emission tomography. So in place of the traditional approach, which again, I repeat, it uses filters placed on both the signal and the idler and to perform frequency resolved coincident measurements, what we do is that we replace one of the two photons with a coherent seed. So this is just another laser, an auxiliary laser, which is shined into the structure together with the pump, which mimics exactly the state of one of the two photons. This will stimulate four-way mixing, so we will have a coherent field, a coherent idler field, which will be emitted by the structure. And again, we scan the frequency of the emitted field with a filter. And we can use also a classical detector, because since now this is a strong field, to detect the intensity. So we can get these very nice shapes. One axis is scanned by changing the wavelength of the seed, while the other axis is scanned by changing the central wavelength of the filter. So it turns out that measuring the modulus square of the joint spectral intensity, which gives the probability of detecting the signal and the idler photon with a specific frequency, is a quite easy task to be done with the stimulated emission tomography. But measuring the full complex joint spectral amplitude, because we have to have in mind that the joint spectral amplitude is a complex quantity, is not an easy task. And you can see, for example, these two optical arrangements that are two experiments that have been done to measure also the phase of the joint spectral amplitude, which involves a lot of optical components. So in particular, we have, it's not sufficient to use a pump and a seed laser as in the scheme shown before, but we have also to use another auxiliary laser and make this laser to interfere with the stimulated field that is generated on the chip. So there are a lot of things to manage with these schemes. That's why we proposed an alternative approach which exploits the capabilities of a silicon photonic chip. So the scheme is the following. So this is a schematic of the chip. We inject light, both the pump and the seed laser, in the same input port. And then we have two Mach-Zehnder interferometers, which are used to let the light to flow just in the upper or in the lower arm of this device. And then in the upper arm, we have a resonator, which is the target device of which we would like to measure the complex joint spectral amplitude. And on the other arm, we have a reference spiral. And then at the output, we have another resonator, which is used to filter the stimulated field to reconstruct the JSA by stimulated emission tomography. So one of the axes is scanned by changing the frequency of the seed laser, while the frequency of the stimulated field is filtered by this ring resonator. So this is a schematic of, this is a microscope image of the photonic chip, and this is how we probe it. So we inject and collect light using a fiber array, and then here we see the photonic chip, which is wire bonded to an external control electronics through wire bonds here, which ensures the reconfigurability, the full reconfigurability of this chip. And then the measurement. So the measurements proceed in 3 steps. So in the first step, we just let light to pass into the resonator source by configuring this Mach-Zehnder to reject the light into an unused arm. And then we use stimulated emission tomography to map the modulus square of the joint spectral intensity of the resonator. So this is the simulation, and this is the one that we measured. Then we do the same, but by configuring the chip in such a way that the light only flows in the lower spiral. And we get this measurement of the JSI and this simulation. And then as a third step, we let the light to simultaneously propagate both in the resonator and in the spiral, and the stimulated idler fields which are emitted are let to interfere to this beam splitter. And when we perform again a frequency resolved tomography, we get this interference pattern, which is the interference between the stimulated field of the signal and of the resonator and the spiral, frequency resolved. And from this two-dimensional interferogram and from the knowledge of the intensity of the JSI of the resonator and the spiral, we can extract the relative phase, the phase of the JSA of the resonator, because this pattern is governed by the mutual phase between the resonator and the spiral. And since the spiral has a joint spectral amplitude which has a flat phase profile along the anti-diagonal, it has no spectral features along the anti-diagonal. The effective phase which is extracted is exactly the one of the resonator, up to an overall offset. There is just one issue to be solved before extracting the phase, and which is the fact that the one-to-one mapping between the stimulated field emitted by the resonator and the complex joint spectral amplitude is only holding if the seed laser in the same asymptotic state of the corresponding photon of the pair. So what does this mean practically? So it means that if this is the asymptotic output state of, for example, a spiral, so it can be thought as an eigenstate of the system, we have to shine to let the seed to propagate exactly in the same eigenstate in such a way that the stimulated idler has an amplitude which is exactly equal to the joint spectral amplitude. While for a waveguide is simple, for a resonator it's not. It's not because the asymptotic field associated to a photon, which is generated by the resonator and detected by in the true port of the resonator, so by this detector, is realized by seeding both the add and the input port of the resonator. While in our configuration, we just seed the resonator in one input port and we detect the stimulated field into the true port. We can demonstrate that we can get rid of this, so we can overcome this issue by nevertheless measuring the amplitude of the complex amplitude of the stimulated idler wave, and by applying a correction factor. So as you can see here, the joint spectral intensity, which is what the quantity that we would like to measure, is proportional to the amplitude of the stimulated idler field. It carries the phase of the idler field, but we have to add a correction factor, which is given by 2 times the phase of the field enhancement of the resonator. So the field enhancement is defined as the ratio between the circulating field inside the resonator and the one which is exciting it. We measured this correction phase. Again, I don't want to enter into the details on how we did that, but by very similar, by using the same setup, we were able to measure both the intensity, both the amplitude, and the phase of the field enhancement, as you can see in these plots, which are showing both. And by doing that, by applying this correction term, we were able to determine the phase profile of the joint spectral intensity. So this is the measured one, and this is the simulated one, which shows a fidelity of 83%. And what is most important, and what gives me a lot of satisfaction, is that around 1 year later, one of my previous colleague realized an upgrade of this photonic chip and measured the same joint spectral intensity of a resonator, but by performing a fully quantum phase frequency resolved phase tomography. He got this phase profile that well reproduce the structures that I found with a stimulated process. But as you can see, this picture that has been obtained by stimulated emission tomography is much more resolved, is much more high resolution with respect to this, which is a quantum mechanical one. And it has been also acquired with a much lower integration time. So, okay, sorry for being quite long. I just write the conclusions. So what we saw in this talk is that we are seeing, or at least I tried to emphasize that to build the universal and noise intermediate quantum architectures, we need to interfere highly pure and distinguishable single photon states. And we can engineer photon sources using intermodal four-way mixing to simultaneously achieve both of these features. And the tools for doing that are given by the engineering of the waveguide mode dispersion by changing, for example, the width or the height of the waveguide, or choosing the right modes. And we can also play with these modes to force an adiabatic switch on and off of the interaction to remove residual correlations. We demonstrated a record on Gummandel visibilities among photons between different sources. And so in our paper, we also demonstrate that with this kind of visibility, a record visibility, we can reasonably think to perform boson samplings, for example, experiments involving around 50 photons, and the complexity of the pattern observed at the output of our boson samplers will not be limited by these metrics, so the purity and indistinguishability, but eventually they will be limited by other degrees of freedoms like loss. And also we have presented a silicon chip which is able to measure the complex GSA based on stimulation emission tomography. And at that time, it was the first time that a GSA of a ring was measured. So again, I would like to thank you, all the people that make this work possible. So I'm particularly grateful to Stefano Paesani, Stefano Signorini, and Alexandre Minus. So Stefano Signorini is from University of Trento, and Paesani and Minus from were from the University of Bristol. And of course, thank you to all of you for the attention.
Okay, so thank you for your great presentation. Just before our Q&A session, I want to say something. This very event, which was presented by Dr. Massimo Borghi, was co-organized by the OSA student chapter of Yerevan State University in Nas, Armenia, the IPR OSA student chapter, SPIE YSU student chapter, Yerevan State University Faculty of Physics, and Student Scientific Society of Faculty of Physics. So thank you. In case you have any questions, please raise your hands and we will answer them all.
I think I can start questions if no one else is still there to start. Thanks a lot for your presentation, Massimo. It was, as always, very great. My question is about the tolerance in waveguide fabrication. So what are the limits in the fabrication that can affect on the final result?
Yes, so in the case of sources that are fabricated using the silicon technology, so SOI wafers, as we did, so the thickness of the waveguide, so the height of the waveguide, is not a concern because it can be regulated, so it can be achieved with a nanometric accuracy. So if the target height is 220 nanometers, it can vary between I don't know, with a variance of like 1 or 2 nanometers in most of the part of the wafer. So it's not a big issue. While, for example, concerning the width of the waveguide, so this is more subject to fabrication variations. So we can say that, for example, in our chip, if we want to maintain a degree of indistinguishability between two sources, we have that the two waveguides have to have the same width within around, if I remember well, 5 nanometer to ensure an indistinguishability which is above 99%. But if an indistinguishability, if we are happy with an indistinguishability which is lower, it's above 95%, let's say, we can relax this tolerance to tens of nanometers. It helps for sure to have a waveguide which is large. It's 2 micron wide in our case, and so both the modes of the wave, so both the fundamental and the first higher order mode in our waveguides are quite far from the vertical boundaries of the waveguide, so they are not so, the refractive index dispersion is not so sensitive to that.
Okay, and which fabrication technique is used for these chips, e-beam lithography or?
For this particular configuration, the deep ultraviolet lithography is beneficial because we have engineered a compact source in a spiral waveguide, and if we had to realize the same chip, so a spiral waveguide using electron beam lithography, we will suffer for sure from increased loss. Due to the intrinsic process, to the intrinsic nature of the e-beam writing process. So, yeah, definitely it's better to use deep ultraviolet lithography for this, to keep the chip compact, and also for large scale fabrication as we aim.
Okay, thank you.
Okay, Dr. Massimo, I have one question. As I saw, you said that if a photon passes through ring resonator, we can detect the past photon in both of the detectors. So how do we solve this problem? I mean, in case of both detections, we can have some losses, yes?
Sorry, can you say it again? I think that I missed the last part. So if we generate photons in a ring resonator, yes, both the photons will exit on both. Let's say, okay, let's consider this example. For example, so you mean that if a pair is generated, a photon pair is generated within the resonator, they will both exit. They will exit in both the waveguides. You said, right? Yes. And okay, so then I missed the last part of your question.
I said if we want to detect, for example, in only in second detector,
okay,
how will we solve the problem of losses?
Okay. So yeah, this is a very good question. So if we multi-port devices in general as this. So this is a multi-port device because we have one port and then there is another one. So we actually have 4 ports in this waveguide, but only let's say 2 are used for escaping the photons. So as we add ports into a device, we lose photons because they can be scattered into these modes, and there's no way to avoid this. So this is why it's not interesting to engineer structures which has a lot of ports. And we can also, of course, also intrinsic losses, so photons that can be absorbed during the circular traveling, can be also represented by an equivalent waveguide that is coupled to this resonator and where photons can escape. So the answer is that we cannot get rid of the fact that photons can be scattered into other ports. So that's an intrinsic, limitation. So a ring resonator has some benefits in the sense that it can help to realize a brighter source because it's enhancing the light which is circulating here. So it's enhancing the probability of emitting the pair. But this comes at the expense. So there is a trade-off behind. And the trade-off is that, for example, in a ring which is in this configuration, in half of the cases, we lose photons into the other port. So it's a trade-off. We will reject the case where, for example, one photon exits into this port and the other into the other port, which are not useful for heralding single photon states.
Okay, thank you for your answer. Does anyone have a question? Okay, I guess no one.
Maybe you have more?
No.
Okay.
I have a question, but I cannot raise my hand.
Yes,
don't raise the hand. I'm raising the hand even if you cannot see it. What was the question now? I was focusing on finding where is the hand, and now I don't remember anymore. But yeah, no, the question is the following. No, okay, Massimo, I was wondering why. You showed regarding the measurement of the joint spectral amplitude. Okay, I was wondering why there is this interest, let's say, in being able to measure that precisely, let's say, the joint spectral amplitude. Typically, it's because you want to see, okay, how it is engineered your state, okay, and in this way, maybe to verify that you engineer, let's say, the state in that particular way. But I was wondering if the need to measure it is only as, let's say, as a to verify how you measure it, or if there is another, let's say, application of the measurement of the joint spectral intensity, joint spectral amplitude. I don't know if I give you my question.
So you mean that there are, for example, I mentioned that it's interesting to measure the joint spectral intensity to assess the purity and distinguishability, but there are other tools for measuring them, which are maybe quicker than that. So no, you're right. So concerning this kind of, let's say, metrics, so for defining the purity and distinguishability, I agree with you that it's not probably the fastest tool and the more appropriate. And so one has to prefer other approaches. But for example, there are also informations that you cannot extract by that are peculiar from this kind of tomography. So for example, let's say that you want to engineer a photonic state in which where you like have a resonator and a device which has a resonator and a spiral which are in series, or a resonator and has a spiral which are in parallel, and then you combine the photon pair probabilities at a beam splitter. So in order to predict how the final wave function, the biphoton wave function will be, you have to know the complex JSA of both the resonator and the spiral, and you cannot predict how pure, how the final state will be just by measuring the purity or indistinguishability with like an unheralded G2, for example.
Yeah, and this is the main, let's say, importance, the main difference with respect to other tools to measure purity and stuff like that. I mean, this is the main, I mean, the most important advantage, let's say, of the joint spectral amplitude is this one, when you want to look at these kind of things that you said.
Yes, so there are also, so another point of interest could be that there are some approaches in which they use Schmidt modes to encode qubit states. So for example, you use just so for example, if you have a photon pair and each of the photon can be in two Schmidt modes, then you can engineer a state which is entangled in the Schmidt modes. So you have two photons which are entangled in the Schmidt modes. For example, both photons are, since both photons are in the first Schmidt mode, and both photons are in the in the second Schmidt mode. So you have a coherent superposition of that, which is a Bell state in the Schmidt mode basis. And if you want to detect, for example, the presence of entanglement in this state by performing tomography, you have to measure the full complex JSA, because the complex JSA will give you the opportunity to decompose it into the corresponding Schmidt modes, and so you can reconstruct the degree of entanglement between them.
Nice.
This is another example of application.
Yeah, in fact, I was wondering if there was, let's say, a kind of measurement, a kind of experiment that you can prepare in which you, let's say, you extract the information on a certain quantum state, or as you said, an entangled state, by looking at the joint spectral amplitude, let's say. And yeah, nice. Thank you.
Probably there are also other applications which I'm not aware. So.
Okay, thank you. I guess we have another question from. Okay.
Thank you.
Please.
If we have still time, Massimo, thank you very much. Very, very nice, impressive talk. The question is the following. What do you think? How does the nonlinearity or how may the nonlinearity of the material that you use for your photonic circuit affect the phenomena that you are looking at, like the ring resonators and the tomography of those? I mean, if it's not silicon, but it's a dielectric with half of the nonlinearity N2, or even one order of magnitude lower, do you think it is still possible or useful to apply this approach to other materials like silicon nitrides or nitrides? And maybe if you think it is sensed to try this in another wavelength range like near infrared, and how challenging it would be and useful it would be.
No, there's nothing special with this range of wavelengths and with this material. So this is an approach that is pretty much universal, let's say. So I'm not seeing fundamental issues on doing the same with in near infrared or with another material. So it's not scaling. So the features will not change by the magnitude of the nonlinearity of the material. We will have to wait for longer integration times if the nonlinearity is weak, but apart from that, there are no issues that I see.
Okay, do you think it's something useful that can be like tried in the future, also in the context of epicus, maybe?
So I think that in the peculiar context of epicus, it will be much faster to use other tomographic tools as the one that Stefano Signorini had in mind, which do not require a full tomography of the state, because even so, if we adapt, if you want to reconstruct the JSA by performing frequency resolved coincident measurements, so a fully quantum mechanical approach, we need to have very high resolution filters, and we have to wait ages to accumulate sufficient statistics because of the predicted, at least, low counts which are coming out from these systems. While if you want to use the stimulated emission tomography, we need a tunable laser and a filter, which are additional resources that we have to control. I think that it will be much faster to perform like an unheralded G2, for example, to measure the purity, which just require a beam splitter that we can implement on a chip, and coincidence electronics that we already have. So we can, in principle, of course.
Okay,
but,
we can discuss. Okay.
Yeah, I think it's pointless.
Okay, thank you.
Okay, thank you very much. Yes, Tatev?
I wanted to ask a question about like nonlinearity. So isn't it possible to dop silicon waveguides, like silicon waveguides with nonlinear materials that you get higher nonlinearity instead of going to longer integration times? I don't know what will happen in terms of noises with longer integration times. Is it always like the same?
In principle, so in principle, yes. I mean, there are examples where they are, it's not a kind of doping, but for example, in order to increase the nonlinearity of silicon nitride, you can realize the silicon nitride more rich of silicon. So you can add, you can vary the chemical composition to change the amount of nonlinearity. So I'm not aware of what you can do honestly in silicon waveguides to increase the nonlinearity further, because already the nonlinearity of silicon is quite high compared to the other CMOS compatible materials that we traditionally use, like silica, silicon oxynitride, silicon nitride, and yeah, probably I don't know. I don't know if what are the, honestly, if they exist, the different approaches. So doping materials which can help silicon to increase the nonlinearity. I don't know.
Okay.
Okay, thank you very much. I have just got another question. Can you please change the slide into the slide of filters?
Into?
Slide of filters, yes.
Slide of filters.
Yes.
What's the slide of filters? In which?
It was in the beginning, I think.
In the beginning?
Yes.
So probably filters, this one. Here we have filters.
Yes, this one. So the question was about quantum physics. Quantum physics states that, I mean, photon is a quantum particle, yes? So can't photon be detected in the detector? I mean, filter can't change its direction, yes? So it will be detected other way.
In this ideal configuration, yes, we assume that these filters is a device which, if the wavelength of the photon is matched with the wavelength of the filter, it's passed. Otherwise, we can say that we can add an additional port. So this filter can be thought as a beam splitter which has a wavelength dependent reflectivity or transmittivity. So you can ensure the unitary operation of also this device. And so we place the detectors, for example, in the transmitted arm. And then if the wavelength of the photon lies outside the transmission region of the filter, it's reflected into another port. And so this is like a non-destructive operation which conserves the total number of photons. So I don't know if I answered to your question, or maybe I didn't understand it correctly, but
yes, you answered. Thank you. Does anyone have any question? No. So for the very end, I have to ask you to turn on your videos so we can take a group picture of today's webinar. Massimo, please, can you turn off the presentation?
Yes. Just a second.
I will take the screenshot.
Oh, okay.
So I just would like to ask everyone not to move, not to speak, because there are 2 pages. I need to quickly smile. Signor, don't move. 1. And the second one is coming soon. Okay.
Thank you very much.
Done.
Thank you everyone for coming to today's webinar. This was the second part of our sequential webinars called Integrated Quantum Photonics. Stay tuned for the next part. We will post about the third part of this sequential webinars. Thank you very much again. This was everything.
Thank you very much, Kim, for the invitation.
Thank you.